In this video, I want to talk about the natural response of a resistor, capacitor, or RC circuit. So the procedure for RC circuit is very similar to that of RL circuits. So here what we have is we have this independent voltage source with the value Vg, and it's a DC voltage source, so it's constant, that is connected to this first resistor R1. We have this capacitor C, and we have this other resistor which we call it R. The one thing that you see here is that we now have a different type of switch. So this switch is not open or close only. This switch basically goes from position A to position B. So what we want to analyze is that what happens if at time t equals 0, we go from position A to position B. So let's just see what the circuit looks like before time equals 0. So if we have the voltage source, we have the resistor, and then we simply have the capacitor. So this is Vg, this one is C, and this one is for t smaller than 0. So you can call this node A now. So if this circuit has been in this situation for a long time, what happens is that all the voltages and currents have now constant values. So everything is settled down, there is no transient variable in this circuit, and we have also this constant voltage that drives this circuit, right? So if you had a sine wave, then the analysis would be different. But for now, we have a constant voltage. This circuit has been in this situation for a long time, so now every voltages and currents are settled down. So if you remember from the equation for the current of the capacitor, it was IC equals C dVc over dt. So that means that if the voltage of the capacitor is constant, the current that goes through the capacitor is going to be 0. So the capacitor is acting as an open circuit. So that means that there is no element between these 2 points anymore, right? So even though you have the capacitor, but the capacitor is acting as an open circuit, there is no current going through it, and since these 3 elements are all in series, there won't be any current in the circuit. So since there is no current going through this R1, basically the voltage drop across it is going to be 0. So what we end up having is the voltage across this capacitor is going to be Vg, and that would be the initial voltage of the capacitor at time 0. Now what we want to do next is that we want to change the position of the switch and move from A to B. So in this case, what happens is that we have the capacitor now being connected to the resistor R, and the left part of the circuit is not going to be connected anymore, because if you have the switch connected here, then this from A to this point is going to be open circuit. So the left part is now disconnected. But what we have here is that we have a capacitor with the initial voltage of Vg. So basically this capacitor has some energy stored in it in a form of a voltage. But we know that the resistor is always consuming power. So intuitively we can determine that if we have a capacitor with some initial voltage or some initial energy that is connected to a resistor that is going to consume all the energy over time, the behavior would be very similar to what we had for the RL circuit, in which we had an inductor with some initial energy stored in a form of initial current, and we connected that into a resistor, and we saw that over time that energy is going to be consumed by the resistor. So we have a similar situation here. So to find the equation, what we can do is that we can now write the KCL for this node. So let's just say we write the KCL for this node. So it is easier to write the KCL rather than write the KVL. Because if you want to write the KVL, you have to find the equation for the voltage of the capacitor, which requires integral. But the current that goes through the capacitor only requires derivative. So this is how we get the first order differential equation for this circuit, by writing the KCL for this node based on the voltage that we have here. So the current that goes to the capacitor is going to be C derivative of V over T, and the current that goes through the resistor is going to be V over R. So as you can see, this is very similar to the equation that we had for the RL circuit. So for the RL circuit, it was L dI over dt plus Ri, which was equal to 0. So other than the variable I having a constant coefficient R, which here we have the voltage divided by R, nothing is practically different. So these two are both considered first order derivative, because the highest derivative that we have is of order 1. So anything else that is different is basically the name of the variable is voltage now instead of being current, and the coefficients are basically a bit different too. But nonetheless, if you follow the same multi-step procedure that we followed for solving this equation, we applied the same procedure here, and considering the differences that we have this equation for the voltage across the capacitor or the voltage across this resistor. You see, these two can be considered to be connected in parallel, so the voltages is the same for both of them. So voltage at any given time equals voltage at time 0 multiplied by e to the power negative t over RC. So this whole thing is for the denominator of the exponent. Considering that the initial voltage is the same for time less than 0 and time greater than 0, and that has to do with the equation for the current of the capacitor. So I repeat that, IC dVc over dt. So the voltage of the capacitor cannot jump or cannot have sudden changes, because that means that we need to have an infinite amount of current. Since we cannot have infinite amount of current in any physical circuit, that means that the voltage cannot change suddenly. The current can change suddenly, but the voltage cannot change suddenly. So because of that, the voltage at time 0 minus or epsilon before 0 equals the voltage at time 0 equals the voltage at time epsilon plus 0. And that is basically Vg, or we can call it V0 as well. So we can replace this in this equation, and what we get is Vt equals V0 e to the negative t over Rc. So now that we have the equation for the voltage, we should be able to find the equations for the current, power, and energy. But before doing that, let's just see what is different here as opposed to what we had for the RL circuit. So for the RL circuit, we defined the time constant as L over R. For the RC circuit, the time constant is R multiplied by C. Their meaning is exactly the same. They both act as the unit of time for a circuit. But now, because of the different ways that the equations for voltage and current are related, the time constant for the RC circuit is actually R multiplied by C. So given this definition for the time constant of an RC circuit, we can rewrite the voltage equation. So now we get V at any given time t equals V0 e to the negative t over tau. As I said, the physical meaning of the time constant doesn't change. So first of all, this voltage equation is again an exponentially decreasing function. And let's say if you have two exponentially decreasing function with two different values of tau, the one with the largest tau or time constant takes longer to get to zero in comparison to the one with the smallest time constant. So now that we have the equation for voltage, we can find the equation for the current as well. So the current that goes through the resistor, and it is going to be the same current that goes through the capacitor too, because we have the capacitor and the resistor connected. You can consider them connected in series. Also, you can consider them connected in parallel too, since there are only these two elements that we have in our circuit. So the current is going to be Vt over R. So V is the voltage of the capacitor, R is the value of the resistor, and it is going to be V0 over R multiplied by e to the negative t over tau. For the equation for the power, we had several variations. So one was Vi. We can also use I squared R, and also we can use V squared over R2. So any of these is fine. But if you use the equation for power is going to be V0 squared over R multiplied by e to the negative 2t over tau. And the reason that we have this 2 is when you multiply V with I, you have two functions each having this exponential term, e to the negative t over tau. So when they multiply by each other, their exponents are going to be added together. And finally, for the energy that is being delivered to the circuit by this capacitor over time, it's going to be the integral of the power over time. So we start from time 0 to t, and if you calculate this integral, you see that this is an exponentially increasing function. But it has a limit too, because when you make the value for t very large, this term becomes 0, and this is going to be simplified to 1 over 2 CV0 squared. And this is exactly the same equation that we had for the energy of a capacitor. So for the energy of a capacitor, we simply had 1 over 2 CV squared. So it's voltage. So since the initial voltage that we have is V0, this is the total amount of energy that was stored in the capacitor. So let's just summarize the procedure for finding the natural response of a RC circuit. First, we need to find the initial voltage V0 across the capacitor. So if we have any switch in the circuit, we need to know what was the situation before the switch changes its position. We should consider that if we have a circuit that has been in a single position for a long time, the capacitors behave as open circuits now. Why? Because if everything is settled down in the circuit, no transient variables, The current of the capacitor is C multiplied by the derivative of the voltage of the capacitor over time. So if Vc is constant, the current that goes through the capacitor is 0. So that means that the capacitor is acting as an open circuit. Then we need to find the time constant of the circuit. The time constant is R, basically the resistance that is connected to the capacitor multiplied by the capacitor. Again, as before, this resistance you can consider it as Req or Rth. It doesn't have to be a single resistor. You can have a circuit that has an equivalent resistance, and that should work fine. And then after doing that, we can use these sets of equations to find out the values for the voltage, the current, power, and energy. So the voltage is an exponentially decreasing function because we have some energy that is being stored in the capacitor, but since the resistor that you connect to it, or the bunch of resistors that you connect to the capacitor with initial energy or initial voltage, those resistors always consume energy. So over time, the initial voltage of the capacitor or the voltage of the capacitor drops because those resistors consume the energy that was stored in the capacitor. The current is also a decreasing exponential function. So it is the power of the capacitor too, because over time, as more energy of the capacitor is being consumed, the amount of power that it can deliver is decreased. On the other hand, the energy is an increasing exponential function, but it has a limit too. So the maximum is 1 over 2 CV0 squared. And the reason for that is we have this power and the energy is the integral over time. So as you can see, over time we are basically summing these the area under the curve for P. So the energy is increasing, but this area is not infinite. So we get to the maximum, which is 1 over 2 CV0 squared. So in this video, you learned how we can calculate the natural response of RC circuits, and also we talked about the time constant of RC circuits.